before I do, there's one thing I want to say about the homework that you're working on right now. So the homework includes things about rotations, rotations and moment of inertia and things like this, torque, but it also includes things like, let's see, like a problem that I remember that was roughly something like this, okay? Where you have some stick and it's attached to a rope and there's a mass hanging off the end and you're trying to figure out stuff about the situation in which this stick doesn't move, okay? This is, I feel like it's homework, problem number 3. I forget what the homework number is. Is it 11 maybe? Don't take this too seriously. It could be 10. I can't remember which one we're on right now. And the thing that I want you to take away from problems like this is it's just like when we were figuring out, like, what does it take for something not to move when you just push on it? Same business, except for this thing not to move, 2 things are necessary. So the first thing is that the sum of forces needs to be 0, including any reaction forces, like from the ground. And number 2, the sum of torques needs to be 0. That's so that it doesn't rotate. So for any problem where something is not moving, and you're asked about, like, well, what does it take for it not to move? The 2 things you should keep in mind is, 1, if it's not moving, then it's not going like this, or like that. So that's a force balance thing. We've done that before. And if it's not moving, in particular, if it's not tipping over, so it's not rotating, so the balance of torques has to be 0. So the sum of all the torques has to go up to 0. Okay? I mean, that's not unique. The fact that you have to think about this is not unique to this particular problem. I'm just mentioning it, okay? Okay, and I'll be available in office hours to talk through these kinds of things. Okay, so another thing that you might find helpful is angular momentum, so I want to get to that today. So last time we began to talk about angular momentum right toward the end of the lecture. So remember, we have this dictionary, okay? The mass is related to moment of inertia. Force is related to torque for rotating things. Velocity gets converted to angular velocity. Acceleration is related to angular acceleration and so on. And we have a concept of momentum with linear motion, mv, right? And there's a notion of angular momentum, which is angular mass, I, times angular velocity, omega. Okay? And last time, I went through these equations, and I basically said that all of this is r times p, where r, I should probably be a little bit more explicit. So here is some axis. Suppose I have some object, and I want to know the angular momentum, L, relative to x. So to motivate this, I mean, you could ask this regardless of what else is happening, but if you want, imagine having this thing connected to x by some stick, which is very, very light. So then it's the angular momentum of this whole thing, okay? But the point is you have to pick where the rotation point is to ask this question for angular momentum. So it is L, well, we're going to make this more precise in a second, but it's r times p, where this is r. That is to say, the length of this thing is r. And this is p. That's its linear momentum. So mass times velocity. Okay, so since you saw this, gosh, when was it? Friday? I wanted to do something else with this. I want to try to explain why this is a useful concept at all. Okay? So the reason it's useful is that just like momentum is conserved, and so keeping track of it is very useful, angular momentum is also conserved. And so keeping track of angular momentum is thus also very, very useful. So, for example, if you start in a situation where nothing is moving, okay, and if you can ignore things like friction and other things that make life very complicated, okay, and you are part of some system, okay, and you start spinning one way, okay, the other part of the system must then spin the other way to keep the angular momentum zero. If it was zero at the start, it's going to be zero at the end. Now, importantly, angular momentum can be negative because it depends on which way you're spinning. Okay, so it's even a vector. We'll talk about that later. So let's see. Okay, I want to, in a minute, give you an example of the use of angular momentum. But before that, I just want to highlight one important thing. In this class, for simplicity, we will almost always focus on the rotation of rigid objects. That is, ones that are not changing their shape as they rotate. Because, well, it's easier, okay? If you're dealing with something soft that can change its shape as it rotates, that's very interesting. Many things in life are like that, but it's much more difficult because if something changes its shape as it rotates, its moment of inertia changes. So you have to think about whether you can actually deal with that. So if you have a spinning figure skater, which I'll work through as an example in a couple of minutes, like they change their shape by pulling their arms in. Again, I'll go through an example of that with numbers and formulas in just a second. What you can do is you can sort of say, okay, if the angular momentum changes from one value to some other single value, then you can keep track of that. If you have to deal with how it changes continuously, it's very difficult. Okay? And I do want to say, though, that non-rigid objects are very interesting. And believe it or not, as soon as you ask about them, all bets are off as to how difficult it is. Okay, I'll give you an example of just how difficult it is. So let's talk about what happens with figure skaters just for a minute, which is a case where they're definitely not like perfectly rigid objects. They can definitely change their shape. That's the whole point. So imagine the following situation. Okay. Here is ice. Here is a figure skater. Okay. Well, okay, sure. And their arms are spread out like that. They're currently, the ice is like coming out as a sheet like this out of the board. Let's pretend. And they are spinning around, okay? And as they do that, they have some moment of inertia. Okay, so they have a moment of inertia I. And as they're spinning around, there is some angular velocity omega. So this is the before picture. So let's see if I can draw a similar picture. Okay, the swipe is their hair. Okay, and then they pull their arms in. What does that look like? Like that. Okay? If you've ever seen real figure skaters, I mean, it's much nicer than this, but okay, whatever. And they're spinning. Okay, they have ice skates. So in this problem, I'm suggesting that we contemplate that as they pull their arms in, the angular momentum changes by a factor of 2. Maybe that's also because they pull their legs in. So let's try it. Let me try to draw that. Okay. So the new moment of inertia is I over 2. So you could ask, what is the new angular velocity? So I just want to highlight that this is actually a really easy problem. Because what you do is you write out the initial angular momentum, which is I times omega. You write out the final angular momentum, which is I over 2 because the mass got brought in, so it dropped compared to what you had before, times omega F. We don't know omega F, but the thing that we do know is if they're not losing momentum and energy to the ice, which if it's slippery enough is going to be good, Li has to be equal to Lf because angular momentum is conserved. So we get Li, which is this. If you stare at these formulas, you'll convince yourself that they will be consistent if this is true. Just imagine plugging this back in. It's all be consistent. So they speed up by a factor of 2. So if you've ever watched figure skaters, you can see them do this all the time because it looks cool. But what they're doing the entire time they're doing this is demonstrating physics. Yes?
Couldn't you also think about it, because it says on the slide that they have to cancel each other out, so if one increases the other.
Yep, that's exactly, thank you. Yes, just as it says on the slide, right? If angular momentum is conserved, so these two things are the same, and this drops by a factor of 2, that has to go up by a factor of 2, which assumes that this doesn't change. And I just implemented that here. Yeah. Now, I rarely have a good excuse to show you any video clips, so I don't know if this will work. Let's try it. Oh, well, it has sound. Okay. Hopefully you can it. There you go. That's a factor of 2. Okay. Wonderful. So, that brings me to a few comments on non-rigid bodies, okay? I mean, figure skaters are, of course, very flexible, but the most prototypical example of a non-rigid body are cats, right? So, if you ever see one, they're likely to be doing something like that, okay? So, well, how do cats move? Well, forget about how they move. Let's talk about how they fall. So there's this thing with cats that, you could hold them. I don't have a good cat. Okay, here we go. So imagine that the bottom of this dry erase pad, the eraser. Suppose the bottom of it are the cat's feet. So if you hold the cat and you gently drop it, well, this thing is not a cat, so it failed. But it will just drop on its feet. Wonderful. Then it'll probably run away and never talk to you again. But imagine you hold the cat upside down. To be clear, only imagine, don't actually do this. But if you hold the cat upside down and drop it, okay, what it will do is it will manage to do something weird in the air, rotate and land. If you think about angular momentum conservation, this sounds weird. How does it do that? So you let it go, it's upside down, angular momentum is conserved, it's not pushing off the air, it's a cat, not a bird. How does it do this? Because it has, how? So, how is it consistent? So this is the kind of silly question that physicists sometimes ask themselves for a living. Okay, this problem is so famous, it has a name, it's called the falling cat problem. People have been wondering about it since 10,000 years ago when they first domesticated cats. And believe it or not, it was not solved until 1969. Okay? And I just want to note that this paper, they said that this phenomenon of cats landing on their feet has given rise to questions of dynamics as well as physiology. And it's received much attention, blah, blah, blah. Okay. So they tried to figure out how it works. It was kind of okay, but not so great. So the basic picture that they came up with is you got to think of a cat as two connected bodies that are separately rigid, okay? But the combination most definitely isn't. So the cat's rear end rotates independently of its front end. I mean, like I said, they're very flexible. I mean, this is clearly a terrible caricature of a cat, but nevertheless, okay, this was the state of the art. Let's see, was it? Yeah, it's these dudes in 1969. So believe it or not, like you could be in the Department of Applied Mechanics writing papers about cats and get paid for it. It's amazing. So I learned about this. Well, I'm not old enough to have learned about it from these papers, but somebody told me about them later. People wrote papers about the square cat, okay, where they model a cat as this parallelepiped where each of the dots represents a hinge and solve that mechanics problem. This was like beyond 1301, okay? So as soon as you deal with non-rigid objects, it gets weird, okay? Right. So there are many questions like, what's the most optimal way of making sure you land on your feet? People studied that. So all kinds of things. It's all very cool. It's all beyond this class. We're never going to touch this after this slide. I just thought it's really funny to tell you that some of the things that we're talking about are like one hop away from research problems. I don't know if it makes you feel better or worse. Probably worse, okay? But anyway, it's also an excuse to draw pictures of cats, so I just did it. Okay, so let's actually do some examples that are relevant to this class. Well, what did we do with momentum anyway, right? So just as a reminder, this is the worst eraser ever. 1 second. Okay. Remember we did collisions? We have a box, we have a box. This box goes at some velocity that's not zero, hits that box which is at velocity 0. Okay, they hit each other, then they bounce off and stuff happens, right? So we talked about this, and momentum was super useful for it. So now we're in a position to understand how rotating things collide. So, okay, let's work it out. So what's happening here? So we have a disk, like this, and there's an axis, okay, and it spins around its center at some initial angular velocity. And now you take a new disk, which is not spinning, and you just drop it on the first disk. So the initial situation is that this disk is rotating. And you have a second disk, which is not rotating. And the final situation is that they rotate together. And so maybe you could be asked to figure out, like, what's the final rotation speed? That's an example of the kind of problem one can do using angular momentum. Okay, so there's a lot going on here. So it's simpler than it looks when I first show it to you like this. So let's set it up and do it carefully and slowly, and you'll see that it's pretty friendly. Okay, so we have a spinning disk initially, right? And in the problem statement, there's no claim about what is the moment of inertia. So let's just go with it, okay? Let's just say, okay, we don't know what the moment of inertia is, but the one thing we know is that it's some number times the mass of the disk times its radius squared. Do you remember that? That's what moments of inertia look like. Okay. So that is for the first disk, this one. And this disk has some radius r. And let's say that this other disk has a radius of r over 2. And otherwise, they are, let's see, they have the same mass. So this one has a mass m, this one also has a mass m, just to make the problem concrete, okay? So then, for disk 1, you're going to get that. For disk 2, okay, has the same shape, it's spinning around the same axis, so the number c, whatever it is, we don't know what it is the same. The mass is the same, but the radius is different. So this is c over 4 mr squared. Is this okay so far? Okay. Okay. So now we can work out the initial angular momentum. So that will be I1 times omega, however fast it was rotating initially. Let's call that omega I. And then we can also record the final angular momentum. So that will be, well, I1 times the final angular momentum. And if they're rotating together, right, if they stick together after the collision, let's assume that. To make it easy. Then the other disk, with its own angular momentum, will also go around with angular velocity omega f. So here is the final angular momentum. So that is I1 plus I2 omega f. Okay, and if angular momentum is conserved, these things should be equal. So let's set them equal to each other and see what we get. Okay. So first let's start with this thing. So CMR squared is equal to this thing. So that is C, oops, I forgot something. I forgot the WI. So this whole thing is the initial angular momentum. Okay. Okay, so we want to know the final angular velocity in terms of the initial angular velocity. So now, there's a c on both sides, so it cancels out, right? There is an m everywhere here, so it cancels out. There is an r squared everywhere, so it cancels out. Okay, let's see what we're actually getting. So we have omega I is equal to omega f okay, so this is 4/4 omega f plus 1/4 omega f, which is 5/4 omega f, and that is omega I. So, but what we wanted was the final angular velocity. So that means we can write omega f is equal to 4/5 omega I. I put that in a box and see if it's anywhere close to what I did when I did it before. It is. Okay, good, good, good. So, now you might be wondering, like, what is the passes the elephant test on the bottom? Like, why is that there? Think about it this way. Imagine you have this disk, and then something falls on it, right? So the heavier that thing is, the more it should slow down. But in particular, it would be totally nuts if you had something spinning and something falls in it and it speeds up. If that thing that fell on it just fell straight down, there's no way. And indeed, we see here, and also on the board there, that the final angular velocity is 4/5, that is 80% as large as the initial angular velocity. So the thing slowed down. This is very similar to how we did collision problems for example, with inelastic, totally inelastic collisions in the past. It's just with angular momentum instead of normal momentum. Anybody have any questions about this? Yes?
Would it be slow down even more if would it slow down even more if the top disk was rotating in opposite?
Yes, it would. It would. So if you make the top disk rotate, that's actually a great extra example to work through. So let's see. Yeah, let's try it. Right? It's given what we've done already, it's a very small change. Might as well get it straight and make sure that your intuition is correct. I agree with your intuition, by the way. But let's just check and see how that works. So let's change it. Okay. So now the top disk is rotating at let's say minus omega. So it's in the opposite direction, but the same angular velocity and magnitude. So let's figure out like what changes. What changes? Right. So the initial angular momentum is now I1 omega I, and then plus I2 omega I, but with a minus sign, right? Because this is coming from the second disk. And then for the final, the expression looks the same as before. And now you can see that whatever this is used to be equal to this thing. But now it's equal to something smaller. Why? Because when we write this thing out, we get I1 minus I2 omega I. And we go back over here. What is I2? It's this thing. Right, so if you subtract these two things from each other, you only get 3/4. You see, 3/4 is less than 1. So you have less angular momentum to share around. So that's guaranteed to drop omega f. Okay, and it would have gone the other way if this disk, the top disk, was spinning the same way. Then it would help speed it up instead. Does that make sense? I'm glad you asked. It was good to do an extra example. Other questions? Okay. So I think that actually motivates the next Dryman question. Bear with me, I need to actually open it for all of you. I hope it's open, but before you do it, let me explain what's going on. So imagine that you are at a playground and you want to get on a spinning carousel. Okay, but it's moving way too fast. It's much too scary to get on it. But you know, you arrived carrying an 80-pound backpack, as one often does. There it is. And you decide to slow down the carousel by throwing your backpack on it. And so the question is, what is the best point to throw your backpack if you want to slow down the carousel? Is it point C, is it point B, or is it point A?
I got a question.
There's a question. Yes, go ahead.
Are you like dropping it on any of those points, or are you throwing it from where you're standing in the picture?
Throwing it from where you're standing in the picture, yeah. So this assumes that one can throw an 80-pound backpack, which is not that easy to do, but for the sake of argument, okay, let's say. I mean, you know, there's some skis on it, there's an ice axe, there's whatever. Yes, another question. Yes, go ahead. Yeah, but on opposite sides, yes. Mhm. Okay. So you know the drill by now. I just want you to try it at first. You can feel free to change your answers. So So look, if you throw it at point A and you throw it at point C, the magnitude of the angular momentum of the bag with respect to the center of the carousel will be the same. But if you throw it there, right, it will try to make the thing go that way, which is to say it will speed it up, which is totally not what you want. On the other hand, if you throw it at point A, the bag will be trying to go that way, right? So it will slow down the disk. But just as in response to a question a few minutes ago, we talked about what would happen if you drop something that's not spinning onto a disk. I mean, that slows it down. So that's what would happen if you dropped it at point B. Effectively, the bag's initial angular momentum would be basically zero, close to zero. If you drop it at C, it would have like the same angular momentum sign as the disk, so they would add. But you wanna throw it at A. Any questions about that? Yes.
What does it mean by or what do you mean by A and C maximizes the angular momentum of the bag?
They maximize the magnitude of the angular momentum of the bag because they're further from the center. So the angular momentum relative to the center of the disk. So that involves the speed of the bag, but also how far it is away from the center. So the further from the center you throw it, the bigger its angular momentum relative to the center. Does that make sense? Okay. So, I should try to explain in a more coherent way than I did the last time I tried it, how directions work with vector products and how all of this really fits together. So let me try. So, at some point, long ago, we met the dot product, A dot B, okay, when A and B are vectors. And the dot product appears, for example, in the formula for work. And the dot product is zero when you have two perpendicular vectors. And otherwise, if they're parallel, it just gives you either 1 or -1. The cross product appears in the angular momentum formula. And it is instead 0 when vectors are parallel. So the magnitude of the cross product is something that you've been using for a bit now. It's just length of A, length of B times the sine of the angle between them. What I want to try to explain, hopefully more coherently than last time, is how do you figure out the direction of the cross product. This is just to say that L is a vector just because it's built out of vectors. Okay? So, right-hand rules. All right? So, this is called Fleming's right-hand rule. I don't know anybody who can do that one. So let's not. Okay? Don't do this. Okay, but there are two other right-hand rules, okay? And you can choose whichever one is convenient to the problem that you're working with, and you'll see why you would choose one or the other in a second, okay? But it is extremely important that in the process you use your right hand and not your left hand, just to get the sign right, okay? So, imagine you have something rotating like that, okay? Then what you're supposed to do is to stick your thumb out, curl your fingers, and curl your fingers in the direction of rotation, and then your thumb will point in the direction of the angular momentum, or the angular velocity. So, for example, if this thing is my rotating object, like this, okay, to get my fingers of my right hand rotating in the direction that it's rotating, right, it's like this, and my fingers go like that, with my thumb sticking out, L is up. If it's rotating like this, okay, the other way, if I try to cross my fingers like that, it doesn't work. I have to do this. And now my fingers go the right way, but now my thumb points down. But watch out. If you use the wrong hand, right, you can see that like rotating this way will give you the opposite sign. So just watch out, you gotta use the correct hand. That's why it's called the right hand rule. Okay, that's one way. This is very useful if you just want to get the angular momentum from the angular velocity or something like that, from the direction of rotation. There's another way, which I epically screwed up the last time I tried to explain it, and somebody